2.2a, basic differentiation rules and rates of change. So whenever you see derivative, and that's going to be for the rest of the class until the end of the year, I need you to think slope, because that's what the derivative is. It's the rate. There are several different differentiation there are several differentiation rules that allow us to find derivatives without using the limit definition. So the long way, which is what we did in the previous sections, we won't have to do that anymore. So I'm going to write down the several notations that we will see, and they all mean derivative. They all mean the same thing. There's basically 5. We're going to see 4 of them. There's one that we're never going to see, but I included anyway. Okay, now the first 4, those are the ones you're going to see the most common. They are the most common. They're the ones you're going to see the most of. The last one, we're not really ever going to see this. I've never seen it anywhere in any textbook. I mean, other than being mentioned as being notation for derivatives, I've never actually seen it be used. So the first, f prime of x, we did that in the previous section. The next one, the one in green, that one you say dy over dx, and it means you are deriving a function y with respect to x, right? Because the variable in our functions are usually x, and the function itself is usually called f of x or y. The third one relates to the first one. Basically, instead of f prime of x, it's y prime. And then the last one, which for whatever reason confuses people, I don't understand why. So here's our function f of x, and we are deriving it because see this stuff in the front here? It's telling me to do that. So d over dx. So d over dx f of x. We are deriving this function. That's what that means. Okay, and that's the notation. So now we get to go ahead and start using some of the shortcuts. And we're going to start off with the most basic of all the rules. And I'm actually we're going to do it first before I tell you what the rule is. So find the derivative of each function. So for a, we're finding the derivative of the function y equals 7. Well, I want to very quickly graph this. All right, so there's the graph of y equals 7. It's just a horizontal line at y equals 7. Now, what is the slope of this line? So think back to Algebra 1. And hopefully you're like, well, it's a 0, duh, right? Yes, the slope is 0. So what this means, since the derivative is the slope, that means that if I were to find the derivative of this function y equals 7, the derivative would be 0. So there you go. Okay, b, same idea. F of x equals 0. That's just y equals 0. So the slope of that line, which is a horizontal line, would also be 0. Therefore, this is also 0. F prime of x equals 0. Now notice, I'm not just writing down 0. I'm actually stating the derivative is equal to 0. You need to do that. You need to show me that. Every time you find the derivative, you're going to use this proper notation. That's what, whenever I ask you for proper notation, this is what I'm referring to. Y equals 7. If you derive that, it's y prime equals 0. F of x equals 0. If I derive that, it's f prime of x equals 0. So moving on with the same pattern, s of t equals -3. I threw in new notation, s of t. Usually we will use that for position. So if I derive this, again, this function is just going to be a horizontal line. So it is 0 because the slope of that function, the slope of that line, is 0. And that is what the derivative is. All right, d. I always like using the examples with pi in it because it confuses people. Usually people think pi, that's a variable. And no, it's not. Pi doesn't change. Pi is what pi equals. Pi is 3.14159, etc., etc. So it is not a variable. Pi is not an x. K, they're stating that k is a constant as well. It's just a number. So this is a number times a number. So if I were to graph this, it would be a straight line as well, horizontal line. And the derivative of this would be y prime equals 0. Now hopefully you see that the pattern is that all of these are equal to 0 because the functions themselves didn't involve x at all. There wasn't any x's here. At the first one we had 7, the second one was 0 by itself, c was -3, and d still included no x's, no variables. So whenever you have just a number, which is referred to as a constant, your derivative is equal to 0. And I'm going to write down the rule now. So there's a rule. If c is a constant, just a number, then the derivative of that constant will always be 0. It doesn't matter if the number is 1,924,000 whatever. It will be 0. So that's the easiest rule of them all. Okay, before starting example 2, I'm actually going to give you the rule. The power rule has to do when we have x's, and x has an exponent of 1 and up. So the power rule is as follows. The derivative of a function where we have an x and it has some kind of exponent, as long as the exponent is 1 and up. So this could be x to the first power, which is just x, or x squared, or x cubed, or x to the fourth, whatever. But to not just use one exponent, I'm just going to use a generic number n. And then the rule is as follows. So you have x to the n. What you're going to do is you are going to multiply the function by your exponent. Whatever that number is, you're going to use that to multiply the whole function. And then your exponent is going to decrease by 1. So you're going to subtract 1 from the exponent. So this is the rule. All right, so let's put the rule to use, I suppose. For a, let's see, f of x equals x cubed. So f prime of x is going to equal, so we have x cubed, and then I use my exponent, which is 3, and I'm going to multiply the whole function by 3, and then I have to subtract 1. So that is 3x squared. All right, so moving on to b. Here we have g of x equals the cubed root of x. Before I actually use the power rule, I need a power. So therefore, the way this is written out is not really conducive to that. So might as well get in the habit now. Whenever there's a squared or a cubed root or any root at all, you're going to want to make that into a fraction, or sorry, an exponent, which in this case happens to be a fraction. So a cubed root of x is actually the exact same thing as writing x to the 1/3 power. Any fraction, the denominator is the root. Okay, so now that I actually have a power to work with, I'm going to go ahead and derive this. So g prime of x equals, so I have x to the 1/3, and I'm going to multiply by 1/3, and then x, and then my 1/3, I'm going to subtract. Now, it's a fraction. I still have to subtract 1. So basically, 1/3 minus 1. See, but it's a fraction, so it's probably better if I work with 3/3, which does equal 1. So 1/3 minus 3/3 is -2/3. So we have -2/3. And of course, I can rewrite this. Sometimes you may have to, or you have to know how to. So this is actually, the 3 on the bottom tells me it's a cubed root. The 2 on top tells me I'm squaring. But the negative tells me that I am making this a denominator of some fraction. So for example, here's my 1/3. See, but since the exponent of this x is negative, that means the x is now down here instead of up there. The -2/3 squared, right? That's the 2. And then the 3 means cubed root. There you go. Right, c. So we have y prime. And before I actually find the derivative here, I want to express that this is -3x over 2, but I can write this, or rewrite this, as -3/2 x. these mean the exact same thing. And writing it as a fraction separate from the variable is sometimes friendlier to look at. Okay, so when I derive this, I'm going to look at my exponent, which is a 1, right? If there's nothing there, you have an exponent of 1. So I have to multiply my function by 1. So that still leaves me with negative 3 halves. Nothing changed because it's the number 1. And then x to the first power, I'm going to subtract 1. So I end up with an exponent of 0. Well, what is x to the 0 power? In fact, what is anything to the 0 power? It equals 1. So now I have negative 3 halves times 1, which is just negative 3 halves. Now, example C is a perfect example to what you used to do in Algebra 1 with any function in this form. In slope-intercept form, you were trained, or were supposed to have been, in Algebra 1 to say, ooh, this is the slope. Whatever number's in front of the x is the slope. So if I have this, oh, look, the slope is negative 3 halves. Well, that was kind of calculus. Okay, so same thing. And C is basically this example. My slope is the number in front of the x. So when you have a lonely x, the x, once you take away one of the powers, it only had one, becomes 1. So it does go away. Not magically, mathematically. Okay? All right, so final one. Again, I want to go ahead and separate the fraction from the variable. So when I derive this one, so f prime of t equals, so 4/5 t squared, but I'm going to subtract 1, and I should have multiplied the fraction by that exponent, which was 2. And so I get 2 times 4 is 8 over 5, and then t. And there you go. All right, last thing I want to say about this is this. If you noticed, and let me get a highlighter. Hopefully you noticed. My original function, the exponent for a was 3, but for my derivative, it was 2. So that went down 1 degree. And that's what's going to happen. Whenever you derive, your original function should be a degree higher than your derivative. For c, the degree was 1, right, because there was nothing here. And when there's nothing, it's basically a 1. So my, oh, I'm trying to write 1 and it won't let me. Oh, I see why. There we go. And then so my derivative has no x at all. For d, the exponent was 2, and for my derivative, it's that non-existent 1 that we don't have to write, but we know is secretly there. Okay, so again, whenever you derive, the derivative is going to be a degree lower than the original function, and that's how it works. All right, example 3, find dy dx. So I'm going to speed up a little. So f prime of x, right? So these equations, or sorry, functions are a little longer. They have a few more terms, but it's still the same process. So 2x cubed, so I'm going to do 3 times 2, which is 6, and then x. And then the 3, I'm going to subtract 1, so I get 2. So that's that first part. Minus 4 times x, right? So negative 4 times x has an exponent of 1, so 1 times negative 4 is still negative 4. And then the 1 minus 1 becomes 0, which means x is just 1. And then I'm done with that. Right? It's just the number in front of the x, just like in Algebra 1. And then plus 5, 5 is a constant, so that's a 0. So this is my function's derivative. I'm done. All right, b. So g prime of x equals, oh look, a fraction. Maybe your eye needs to see it like this. Negative 1/2 x to the 4th. Okay, maybe that's friendlier, right? So now, let's see, 4 times negative 1/2 is negative 2 x, and then subtract 1, so 3. Plus 3 times 3 is 9 x, and then squared. Minus, it's just a number in front of the x, 2. And there you go. Example 4. All right, so hopefully you're looking at this and you're like, this looks a little different. Because it is. It's supposed to be anyway. Because of this little dude and this little dude. Okay, there are 2's there that I did not mention earlier when I went over the notation for derivatives. And that is because this is the notation for the second derivative. Okay, so this means the second derivative. What we have been doing is finding the first derivative. You mean there's more than one? Yes. Um, Officially, there's 3. We do 2 in this class. So the second derivative, well, we use 2, but we can find whatever one I ask you to find. So that means we're not going to derive just one time, we're going to derive twice, using the first derivative as my new function to find the next derivative after that. Because if it makes sense, the second derivative should be the first derivative of the first derivative. You're like, what? I hope I didn't lose you there, but so this is what I'm saying. Here's my function y. I'm going to find the first derivative. So let's see, x to the 5th is now 5 times x to the 4th. And then the negative 3x cubed is now negative 9x squared. And the 7 becomes 0. So there's my first derivative. Now I'm going to use my first derivative to find my second derivative. And what I was saying was, see, for the second derivative, the first derivative, right, is the original function. And then for my second derivative, it'll be the derivative of that, right? So I derive this and I get this. I derive my first derivative and I get that. So the second derivative is the first derivative of the first derivative. That's what I was saying, which is a concept that's really, really important to understand. Because it'll make your life easier if you can get that, oh, the first derivative is that is the original function of the second derivative, basically. Well, anyway, so 4 times 5 is 20, and then 4 becomes a 3, and then 2 times 9, so minus 18, and then the x squared becomes an x. And again, please pay attention, very close attention, to the degrees. This was to the 5th power. After doing the first derivative, I was down to the 4th power. And then after doing the second derivative, I was down to the 3rd power. Okay? The degrees should decrease by 1. All right. Example 5, determine whether the function is differentiable. Okay, so in order for a function to be differentiable, it has to be continuous before I can move on. So I'm going to check to see if these are differentiable, but they first have to be continuous. So I first have to just establish that the function is continuous. And then once I've established that, then I can go on and figure out if they are differentiable. Okay, so if you recall, continuity can be established by the left and the right hand limits being the same. So x is less than 2 or equal to, and x is greater than 2. So here are my left and my right. So I'm going to go ahead and set them equal to each other. And if they are equal to each other, then I can say this continuous, and that'll check out, and then I can move on and figure out if they are differentiable. So now I'm going to plug in my 2, because that's where we're at, right? 2. So 2 squared plus 1 equals 4 times 2 minus 3. So 2 squared is 4, plus 1, that's 5. 4 squared, 4 times 2 is 8. 8 minus 3 is 5. So, yes, this function is continuous. So now I'm going to see if it's differentiable. Now, for differentiability, I need the derivative. I currently do not have the derivative. I have the piecewise function, the original. So we're going to have to derive it. So x squared plus 1 becomes 2x. 4x minus 3 becomes 4. And we are still looking at x being less than or equal to 2 and x being greater than 2. So now what we have to do is see if these two are equal. So 2x equals 4. I'm going to go ahead and plug in my 2. So 2 times 2 is 4, which yes, because 4 equals 4. So this now checks out. And is this function differentiable? Yes. Okay, it is differentiable. And because I figured out first that it was continuous, I was able to move on to check differentiability. If this function had not been continuous, then I could have stopped right here and I wouldn't have to do anything else because it has to be continuous in order for it to be differentiable. All right, so now we're going to move on to the other example. Now for here on B, I have a square root. So we're going to want to probably change that to 2 times x to the 1/2 power, because that means the same thing. Okay? Okay, so again, I need to establish continuity. So left and right. So let's see, 1/2 x plus 2 needs to equal 2 times x to the 1/2. Well, actually, you know what? I take that back. For continuity, the square root works just fine. Okay, so 1/2 x plus 2, I'm going to plug in the 4. So 1/2 times 4. I certainly hope you're not asking where'd you get the 4 from, right? Hopefully. So 1/2 times 4 plus 2 equals 2 times the square root of 4. So half of 4 is 2, so 2 plus 2 equals 2 times 2, so 4 equals 4. So yes, continuous. So now I want to go ahead and figure out is it differentiable. Okay, so now is when I want to use this. Because it'll be, I guess, friendlier, right? So 1/2 x, oh, hold on. Totally forgot what I was doing. So f prime of x equals, all right, so 1/2 x plus 2. Ooh, this is in slope-intercept form, right? So the derivative, the slope, is 1/2. For the other, let's see, we're going to do 1/2 times the 2, which is just 1, times x, times, or x to the, okay, so we have x, and then I have to subtract an exponent. So 1/2 minus 2 over 2 equals negative 1/2. So basically I have x to the negative 1/2 power, which is the same as saying 1 over the square root of x. The negative makes it the denominator. The 1/2 means square root. And we're still doing this at 4. Okay, I need to go down a little bit more. All right, so now I just plug in, set them equal to each other, and plug in my 4. So I have 1 over the square root of 4. So I have 1/2 equals 1/2. And this is true, so therefore it is differentiable. Again, if this part had not checked out, if this had been like a 9 equals 4, then I would not have to go any further. Okay, so there aren't any practice problems for this section. You actually need to watch the second part of the video, 2.2b.